Hello everyone, good evening. Good evening everyone. I hope everybody is enthusiastic to learn thermodynamics. I am also enthusiastic to support your learning. Okay, in this live session, I am going to solve problems on entropy. For theory concepts, all of you please buy Ekeeda videos where you can definitely understand the concepts very well. And if you have any questions during this 8 to 9 time, you can send message through this live session only, or in this YouTube messaging. If you get any questions after this time, that is from 8 to 9, after 9, you can send a WhatsApp message to the number which is available on the screen. And all of you buy Ekeeda videos for theory concepts. Okay, I will start solving this problem by saying thanks to Ekeeda for creating this platform to reach students through this way. So in this problem, the 5 kg copper block at a temperature of 200 degrees Celsius is dropped into an insulated tank that contains 100 kg of oil, that is at a temperature at 30 degrees Celsius. Find the increase in entropy of the universe due to this process when copper block and oil reach thermal equilibrium. Assume that specific heat of copper and oil are respectively 0.4 kilojoules per kg Kelvin and 2.1 kilojoules per kg Kelvin. So in this problem there is an insulated tank. Let us assume an insulated tank. This contains oil. This oil is at a temperature of 30 degrees Celsius. This oil is at a temperature of 30 degrees Celsius, and its mass is 100 kg, and its specific heat is 2.1 kilojoules per kg Kelvin, and there will be a copper block. Its mass is 5 kg and is at a temperature of 200 degrees Celsius, and its specific heat is 0.4 kilojoules per kg Kelvin. When this copper block is dropped into this oil, definitely this copper block has a temperature more than the temperature of the oil. Here okay, somebody has asked the meaning of entropy. See, entropy is just an unavailable or unavailable energy that in case of a cycle. For example, if some 5 kilojoules of heat is supplied to an heat engine, and that will convert 2 kilojoules of heat into work, and remaining 3 kilojoules of heat is rejected to this heat sink. Here 3 kilojoules of heat is unavailable energy, and measure of this unavailability is this the concept of entropy. Here entropy is a property. Application of first law of thermodynamics to a process gives the property that is called as internal energy, and application of this second law of thermodynamics to processes will give a property called entropy, and that is a brief explanation about entropy. For detailed explanation, please buy Ekeeda videos. So in this case, when this 5 kg of copper block, which is at a 200 degrees Celsius, when it is dropped to this oil, which is at a temperature of 30 degrees Celsius, definitely temperature of this copper block is higher than the temperature of the oil. So heat transfer takes place from the copper block to this oil. In doing so, the temperature of the copper block decreases, whereas temperature of the oil increases, and both reach an thermal equilibrium state, that is the intermediate temperature of both copper and oil, which are respectively 230 degrees Celsius. To find out the change in entropy of the universe, or increase in entropy of the universe, that intermediate temperature is required. To calculate that intermediate temperature, we will have an energy balance, that is heat rejected by copper block is equal to heat absorbed by oil. Heat rejected by copper block is given by mass of copper into specific heat of copper into initial temperature of the copper, Ti of copper, minus T intermediate is equal to mass of oil into specific heat of oil into intermediate temperature minus initial temperature of oil. So here mass of copper block is 5 kg, and specific heat of copper block, it is given as 0.4 kilojoules per kg Kelvin. Here the specific heat of copper block is in kilojoules per kg Kelvin, and specific heat of oil is also in kilojoules per kg Kelvin. So let us take 0.4 directly, that is in the kilojoules per kg Kelvin. So 5 into 0.4 into initial temperature of copper is known, that is 200. It is equal to in the Kelvin scale, this becomes 473 Kelvin, that is 200 plus 273 is 473 Kelvin. Similarly, the temperature of the oil, initial temperature of the oil, which is at a 30 degrees Celsius, that will be in Kelvin as 303 Kelvin, that is 273 plus 30, it is 303 Kelvin. So here initial temperature of copper is 473, it is in Kelvin, minus T intermediate has to be calculated, that is equal to mass of oil is 100 kg into specific heat of oil is it is given, that is 2.1 kilojoules per kg Kelvin. It is 2.1, as I already told you, both have in kilojoules per kg Kelvin. So let us take the values same as it is, as the kilo in the left and right hand side respectively get cancelled. Then into T intermediate minus initial temperature of oil is this 303 Kelvin. So it is 303 Kelvin. Then the intermediate temperature is equal to that value is calculated, and that value is 304.6 Kelvin. So this is the intermediate temperature. Now let us see the change in temperature of copper block and oil. In case of copper block, temperature is increased from not increased, temperature is decreased from 473 Kelvin to 304.64 Kelvin. But for as oil, the temperature is increased from to 304.6 Kelvin. As I told you, here the temperature of the copper. So when the copper is dropped to the oil, which is at a lesser temperature than the heat transfer takes place from copper to copper block to oil. So after some times the temperature of the copper block decreases and temperature of the oil increases, and they reach an intermediate equilibrium temperature, and we have calculated the temperature is this 304.6 Kelvin. So in brief, copper temperature is decreased from 473 Kelvin to 304.6 Kelvin after heat transfer, and the temperature of the oil is increased from 303 Kelvin to 304.6 Kelvin after once again heat transfer. Now to find out the increase in entropy or change in entropy of universe, that is given by change in entropy of copper plus change in entropy of oil, change in entropy of oil. I'll get back to you within a few minutes. Okay. So the increase in entropy of universe is given by uh, delta S universe is equal to delta S copper plus delta S oil. Now let us find out delta S copper and delta S oil separately, and for that we have a equation like this. Delta S copper is given by mass of copper into specific heat of copper into ln. Here temperature is changed from 473 Kelvin to 304.6 Kelvin. Here 304.6 Kelvin is final temperature and 473 is initial temperature. Here it is final temperature divided by initial temperature. Final temperature is intermediate temperature divided by initial temperature is Ti of oil. Now let us substitute the values for these things. Then we will have a delta S for copper. So the mass of copper, it is known that is its value is 5 kg, and its specific heat is 0.4 kilojoules per kg Kelvin, and then the temperatures are also known. Then so the mass of the copper is 5 kg. It is 5 into specific heat is 0.4 into ln. The final temperature means intermediate temperature of the copper. So here we are calculating for copper. So let us take initial temperature of copper. Then the initial temperature of copper is it is 473 Kelvin. Final temperature is intermediate temperature, and the temperature is given by 304.6, and that change in entropy for the copper is given by minus 0.8801. The unit for this entropy change is kilojoules per Kelvin. It is kilojoules per Kelvin. Here one thing that is to be observed is heat is transferred from the copper block to the oil. So there is a decrease in the entropy of this copper block. There is a decrease in the entropy of the copper block. So we have a symbol, that is a negative symbol that is mentioned here. And now let us find out delta S for oil. First is copper, then the next one is delta S for oil. For that we will have the formula same as the previous one. We will have mass of oil into specific heat of oil into ln. Here once again temperature is increased from initial temperature, that is 303 Kelvin, to intermediate temperature 304.6 degree Kelvin. So final temperature is 304.6 Kelvin and initial temperature is 303 Kelvin. So here it is ln final temperature divided by initial temperature. So final temperature is intermediate temperature divided by temperature of the initial at for oil. So for this case we will have once again mass of oil. It is given as 100 kg into specific heat of oil is 2.1 kilojoules per kg Kelvin, then into ln. Here once again it is intermediate temperature, that is final temperature. It is 304.6 0.6 divided by initial temperature of oil is 303 Kelvin, and then after calculation we will have this value as 1.106 kilojoules per Kelvin. Here now let us discuss how exactly this kilojoules per Kelvin is coming. Here the mass as a unit of kg and specific heat as a unit of kilojoules per kg Kelvin, and inside the LAN the temperatures have a unit of Kelvin by Kelvin. So this Kelvin get cancelled, and kg get cancelled. We will have the unit kilojoules per kg Kelvin. This is kilo, then joules per Kelvin. Here K is small k in the kilo, and in the Kelvin that K is capital K, that is usually followed. Now let us find out delta S or increase in entropy of universe, and that is given by delta S universe is equal to delta S of copper plus delta S of oil. Now delta S of copper it is calculated, it is minus 0.8801 kilojoules per Kelvin. So let us substitute here, it is minus 0.8801 plus delta S of oil, it is 0.106 kilojoules per Kelvin. Then the answer we get is 0.2258 kilojoules per Kelvin. So this is the increase in entropy of the universe when the copper block which is at a temperature of 200 degrees Celsius is dropped to the oil which is at a temperature of 30 degrees Celsius. So this is what exactly happens. Any questions are there, feel free to ask. I will answer those questions. Before moving to the next question, if you have any questions during this time, you may ask here itself, or if you get any questions after 9 o'clock, you may send a question to the WhatsApp number that is available on the screen, and I will answer that question afterwards. And once again, I'm informing you to buy Ekeeda videos for theory concepts. Here I am solving problems related to those concepts, and in the next problem which is displayed on the screen, here we have to estimate the change in entropy of the universe due to each of the following processes. There are two processes. The first process is there will be a copper block which has a mass of 0.5 kg, and it is at 100 degrees Celsius, is placed in a lake of water that is at 100 degrees Celsius. And in the second case, two such blocks which are at 100 degrees Celsius and 0 degrees Celsius respectively are joined together for copper specific heat is given by 0.393 kilojoules per kg Kelvin. So in this problem, let us take the first sub question. Here also we should find out delta S for universe, or For that we will have this general formula, that is for the first sub question, delta S universe is given by delta S of copper block plus delta S in case of lake. So delta S universe is given by sum of change in entropy of copper and change in entropy of lake. Here to find out the delta S of copper, that is change in entropy of copper, we need the temperature of initial and final. So for that let us have the temperature change for this first sub question. Here copper block has a mass of 0.5 kg, so that mass of copper is 0.5 kg, and the another data which is given is specific heat is 0.393 kilojoules per kg Kelvin. So here the temperature of the copper is initially at 100 degrees Celsius. Let us take it as initial temperature of copper as 100 degrees Celsius, and that is equal to 373 Kelvin. 100 plus 273 is 373 Kelvin. So when the copper block of mass 0.5 kg which is at 100 degrees Celsius, when it is placed in a lake, let us consider a lake. Lake has a very large amount of water, and this lake is at a temperature of 10 degrees Celsius, and there is a copper block which is at a temperature of 100 degrees Celsius, and its mass is 0.5 kg, and its specific heat is 0.393 kilojoules per kg Kelvin. When this copper block is placed in this lake water, obviously temperature of the block is higher than the temperature of the water. So heat transfer takes place from this block to this water. Here the water is very large compared to the mass of the copper block. So here the water in the lake acts as a large thermal reservoir, so its temperature will not change when there is heat transfer from this block to this large thermal reservoir. So that is what exactly explained in the definition of thermal reservoir. A large thermal reservoir will either receive or supply heat without change in its temperature. That is the very important characteristic feature of this thermal reservoir. So in that case the temperature of the copper block is changed from 100 degrees Celsius to this 10 degrees Celsius. But whereas in the case of the previous problem, since there was a limited quantity of oil, its temperature was also increased, and finally there was an intermediate temperature at which both the hot and cold reaches equilibrium. But whereas in this case intermediate temperature concept will not be there, as the temperature of the water will not increase as it acts as a large thermal reservoir. So the temperature of this copper block is changed from 100 degrees Celsius to T2 is 10 degrees Celsius. That is nothing but 283 Kelvin. So here initial temperature of the copper block is 373 Kelvin and final temperature is 283 Kelvin. So to find out the change in entropy of copper, that is given by mass of copper into specific heat of copper into ln. Here final temperature is T2 divided by initial temperature is T1. Here mass of copper is 0.5 kg and the specific heat of copper is 0.393 kilojoules per kg Kelvin into ln T2 is 283 Kelvin divided by T1 is 373 Kelvin, and this delta S for copper is given by 0.054 kilojoules per Kelvin. So this is the change in entropy for copper. Now let us find out change in entropy of lake, that is delta S of lake. Here change in entropy of lake takes place at a constant temperature, and for that change in entropy formula is given by Q divided by temperature that is to be taken is T2. Here at constant temperature of T2 this change in entropy is taking place. Here we know this temperature T2 that is 10 degrees Celsius. In the Kelvin it is 283 Kelvin, but we don't know Q. That Q is given by heat rejected by this copper block is equal to heat absorbed by that water, and that heat rejected by this copper block can be calculated using this formula, that is Q is equal to mass of copper into specific heat of copper C, then C specific heat of copper into its initial temperature T1 minus T2, that mass is to specific heat of copper is 0.393 kilojoules per kg Kelvin into T1 it is 373 Kelvin minus 283 Kelvin, and that heat transfer Q is given by 17.685 kilojoules. 17.685 kilojoules. Now let us substitute this one to here. So here Q is 17.685 kilojoules divided by T2 that is temperature of the water, it is 283 Kelvin. 17.685 divided by 283, this value will be 0.0624 kilojoules per Kelvin. Here there is no doubt. Heat has a unit of kilojoules, temperature as unit of Kelvin. See, this heat as kilojoules, this temperature as Kelvin, kilojoules per Kelvin. So delta S for lake is 0.0624 kilojoules per Kelvin. Then the delta S for universe can be calculated by summing up these two. So delta S for universe is equal to minus 0.054 plus 0.0624, and this value is given by 0.0084 kilojoules per Kelvin. So this is the change in entropy of the universe in case of the first sub question, where copper block of mass 0.5 kg, which is at 100 degrees Celsius, is placed in a lake of water at 10 degrees Celsius. And for the next one, that is two such blocks. Here in this case, both are copper blocks. They have same mass and they have same specific heat, but the temperatures are, one has 100 degrees Celsius and the other one is 0 degrees Celsius. When they are brought together, what is the change in entropy of the universe that is to be calculated? So the next case, that is the second one. Here also we should find out delta S of universe. In this case, let us take delta S1 for change in entropy of hot copper block, and then delta S2 is change in entropy of cold copper block, that is at 0 degrees Celsius. Now let us have the temperature changes. Here the temperature of the hot copper block decreases when it is brought in contact with the copper block which has a temperature of 0 degrees Celsius, and similarly temperature of the cold block increases, and they both reach intermediate temperature, and that intermediate temperature is very much required to calculate the change in entropy of universe. So for that, now let us calculate that intermediate temperature. For that, once again we will have the formula. Heat rejected by a hot block is equal to heat received by cold block. So heat rejected by hot block is equal to heat received by cold block. In doing so, both will reach an intermediate temperature. So for that, let's have this one. Let's have three temperatures which are T1, T2 and T3. Here let us take T1 is equal to 100 degrees Celsius, and let us take T2 as intermediate temperature, and T3 as the temperature of the cold block which is 0 degrees Celsius, Now let us find out what is this T2, that is intermediate temperature, and for that we have the formula mass of copper block. Here both the blocks have same values of mass and specific heat. So mass of copper block into specific heat of copper block into initial temperature of this hot copper block is T1 minus intermediate temperature is T2, that is equal to, once again, mass of copper block into specific heat of copper block into intermediate temperature minus initial temperature of the cold block. So here this mass specific heat on the left hand side and mass specific heat on the right hand side get cancelled. So here T1 it is as you know, it is 373 Kelvin minus T2 is to be calculated, that is equal to T2 minus 0 degree Celsius means it is 273 Kelvin, and if we calculate the T2 using this formula, let us do that. 373 minus T2, that is equal to T2 minus 273. If that is solved, we will have an intermediate temperature of 323 Kelvin. So here intermediate temperature is T2 is equal to 323 Kelvin. So now let us list the change in temperature for hot and cold blocks. See, for hot copper block, temperature is decreased from 373 Kelvin to 323 Kelvin. For hot copper block, temperature is changed from T1 to T2. It is Ti is initial, T2 is final. So Ti, that is initial temperature, T1 that is 373 Kelvin, and after heat transfer its temperature changed to intermediate temperature T2, and that value we have calculated 323 Kelvin. Here this temperature is very much required to calculate the change in entropy of individual element to have final and initial temperature. And for similarly cold copper block, cold copper block receives heat, so that its temperature increases from initial temperature of 273 Kelvin, that is 0 degree Celsius, to intermediate temperature of 323 Kelvin. So initial temperature for hot copper block is 373 Kelvin, final temperature is 323 Kelvin. For cold copper block, initial temperature is 273 Kelvin and final temperature is 323 Kelvin. Now let us calculate delta S1 and delta S2. As I already told you, delta S1 is a change in entropy of hot copper block. So delta S1 is equal to mass of copper block into specific heat of copper block into ln final temperature divided by initial temperature. Final temperature is T2 for hot copper block and initial temperature is T1. So here mass is 0.5 kg into its specific heat is 0.393 kilojoules per kg Kelvin. It is 0.393 into ln T2 is 323 Kelvin divided by 373 Kelvin, and if there are any changes in the values, you can mention that one in the chart. So it is minus 0.028 kilojoules per Kelvin. This is delta S1 is for change in entropy of a hot copper block, and delta S2, it is change in entropy of cold copper block, that is mass of copper block into specific heat of copper block into ln initial temperature, final temperature divided by initial temperature. So in this case also, for cold copper block, initial temperature is 273 Kelvin and final temperature is 323 Kelvin. So here it is T2 divided by T3. So here T2 is 323 Kelvin and T1 is 273 Kelvin. So mass of copper block is 0.5 into 0.393 into ln T2 is 323 divided by T3 is 273 Kelvin, and this value is equal to 0.0 kilojoules per Kelvin, and delta S universe is plus delta S2, delta S universe minus 28 plus 0.03304, and this value is equal to 0.00504 kilojoules per Kelvin. So this is the change in entropy of the universe when the two copper blocks which are at a temperature of 100 degrees Celsius and 0 degrees Celsius are brought in contact. So that is about the second sub question. For any questions, you can send a message. I'm expecting messages from your side, and once again I'm solving only problems. For all theory concepts, you buy Ekeeda videos. All of you please buy Ekeeda videos, and after that problem I will take another one, next problem. In this case, a reversible heat engine operates between three constant temperature reservoirs A, B and C, which are actually at 600 Kelvin, 400 Kelvin and 300 Kelvin respectively. That reversible heat engine receives 2500 kilojoules of energy as heat from reservoir at 600 Kelvin, and that will do 1000 kilojoules of work. Determine the magnitude and direction of the heat interactions with reservoirs B and C. For this, I'll write down the block diagram for this case. There are three named as A, B and C, and the temperatures are also given 600 Kelvin, 400 Kelvin and 300 Kelvin respectively. So first I will have three heat reservoirs which are named as A, B and C. A, B and C, and their temperatures are it is 600 Kelvin, and the temperature of the B is 400 Kelvin, and the temperature of the C is 300 Kelvin, and these reservoirs are in interaction with a reversible heat engine. It is a reversible heat engine, and this will produce some work, and that is given by 1000 kilojoules, and the work done is given by 1000 kilojoules. And another very important thing here, it is this heat engine receives 2500 kilojoules of energy as heat from reservoir at 600 Kelvin. So from this 600 Kelvin, this heat engine receives 2500 kilojoules. We should find out Q2 as well as Q3, and also their directions. That is very important thing. For that, I will start with energy balance. Energy balance. Here, if we do energy balance at this heat engine, here Q1 is entering heat engine, and that is equal to W. Here work is coming out of this heat engine, but we don't know the magnitude and direction of Q2 and Q3. But let us consider on the right hand side of this equation, if we get the final answers of Q2 and Q3 in positive terms, then the direction of the heat transfer as per this equation, it is from the heat engine to the heat reservoirs. But if their values are negative, then that has to be transferred to this side, to the left hand side. If one of these is negative, that is to be transferred to the left hand side. Then if it is with this one, then heat is transferred to the heat engine. So now let us see the sign after after solving this problem. So for that, let's have this first one, that is Q1 is 2500 kilojoules, that is equal to W is 1000 kilojoules plus Q2 plus Q3. Now Q2 plus Q3 is equal to 1500. 1000 is brought to the left hand side, becomes like this. Now this is energy balance. Now let us do entropy balance, that is heat transfer divided by the temperature at which the heat transfer takes place. So that entropy balance, I will do entropy balance now. That entropy balance is Q1 by T1 is equal to Q2 and Q3 on the right hand side in the energy balance. Here also in the entropy balance, we have to take it on the right hand side. So this will be Q2 divided by T2 plus Q3 divided by T3. Now let us substitute Q1, T1, T2, T3. So Q1 it is 2500 divided by corresponding temperature is 600, that is equal to Q2, it is not known, divided by corresponding temperature for Q2 is 400 Kelvin. Now let us take it as this one as T1, this one as T2, this one as T3. So Q2 divided by 400 plus so has to be calculated, divided by T3, it is 300 Kelvin. And if we rearrange this one, we will get the expression like this, that is 3 Q2 plus 4 Q3, that is equal to 5000. Now if we solve this equation, if we take it as 1, and another equation, if we take it as equation 2, by solving these two equations using the calculator Q2 is equal to 1000 kilojoules. So I have to stress that the symbol here, it is plus 1000 kilojoules, and Q3